Hello, this is our final project summary of our project was feature space steganography for safe MRI-CT translation. Basically, we are doing multimodality translation between MRI and CT as both have their own advantages and disadvantages, so we can have one from another based on our requirements. Standard models like Pix2Pix tends to hallucinate on these type of tasks. So we are using a different type of approach, which is steganography based models. It This tries to suppress this type of hallucinations. The dataset we are using is SynSat 2023. It is a publicly available dataset. It has different types of MRI and CT, paired MRI of CT of over 300 patients. The regions that are covered are brain and pelvis regions. So these are some existing implementations that exists. First is Pix2Pix. It is a paired image-to-image translation framework that uses direct pixel level mapping, and it uses a unit generator use and adversarial loss. The limitations for this model is it assumes that we have a pixel level mapping like bijective mapping between both target and input domains, but in MRI and CT scans we do not have this type of mapping. So we trained this on our data set. We have trained it for two experiments. Next, experiment one is using paired modalities, so both modalities belong to the different same person. The results are very poor, we can see, and for unpaired one these are also not very good. So second architecture that we studied is StegoCAN. StegoCAN uses a cycle CAN type of training, right? But it additionally add a steganographic module that uses steganography to suppress the hallucinations. This when we input our image, then in the feature space it takes the input, the embedding, and generates a mask based on the what features are matchable and unmatchable for in the target domain. So by using this we think we can suppress the hallucinations, but the problem for this model is it is designed for 2D architectures, but we that's why we need to extend it to 3D. So when we extended it to 3D, by replacing all the 2D convolution with 3D convolution and all 2D up convolutions with 3D up convolutions, the results was still poor, and we identified the problem, and the problem Ashmit will tell.
So the first problem was that the mask generation was failing. A real mask and fake mask were not matching at all. So we need to increase the complexity of the mask generating network. Initially, it was a simple CNN architecture. So we first modified it to a proper encoder-decoder network that has convolution blocks with multi-resolution feature extraction, and we also allow skip connections. And in the upsampling layer, we have a channel attention module which helps to increase the complexity of this network. And we were able to generate proper mask using this, but still the results were very poor. So it comes down to the network architecture itself. To explain why it's the architecture, we try to use the full force of dataset. And next, we also applied a bijective loss, which is usually missing in a cyclic GAN architecture. Even with the addition of this bijection loss, we were only able to increase it by 4.5, and the P star was still around 14.5, so it's not too good. And as we can see, the result is pretty blurry. So we need a different architecture that is more specific for 3D instead of a 2D extension of a 2D architecture. So we were looking for better works on 3D domain, and this is a recent work of VICV25. It's specifically designed for 3D modality. It has multi-resolution input and output, so it has supervision over multiple resolutions. The unit has a very dense skip connection networks, which allows very proper gradient backflow. And in the upsampling layer, we have a convolution block attention, which basically disintegrates two attention modules. One is the channel attention and one the spatial attention. Also, we have fixed voxel-wise supervision on the output of the discriminator. So basically, we have multiple resolution of outputs of discriminator which are being supervised. This type of network was already working well over 3D modality and produced very good results. So initially, it was trained on T1 to CT, HCP, and BRADS. We extended it for MRI to CT on Synthra dataset. The overall architecture was something like this. We have two generators. One converts CT to MRI and one converts MRI to CT, and these are trained independently. The problem is that it requires bijective mapping of paired datasets, which we actually have, but for extension, we try to remove it. So the results on this particular architecture were pretty good. We were able to get a PSNR of around 31, and the ground truth generated and the ground truth and generated CT were matching pretty well as well. So the next goal was to remove this bijection mapping and allow for non-paired dataset. And that's where the cycle GAN training comes in. Next, we try to apply a cycle GAN training of this MAD unit architecture. So we have two cycles, forward cycle and backward cycle, as in the standard plan implementation, which converts real MRI to fake CT and then to reconstructed MRI. And similarly here. Now, the problem with this is that cycle GANs again hallucinates feature and it passes these hallucinated features of original MRI into CT, which should not be there. This is because it during reconstruction it requires some extra information and it hides this extra information in the generated CT itself, and this causes these artifacts, and it also reduces our overall PSNR. So the solution to that was steganography, which we already explained. We have an input image, and we divide it into two parts of features which are matchable and features which are unmatchable using a mask generating network. From these matchable features, we pass it to the second generator and we get the image of the second domain. And you use these unmatchable features to during the reconstruction, because the reconstruction network actually requires this unmatchable features. Now, to explicitly make the network focus on these unmatchable features, we add noise to this generated network, which explicitly destroys the steganography or hidden information travel from this path flow. So the results were very nice, and we were able to actually solve the hallucination problem and artifact. The generated results did not have any artifacts at all, and the unpaired dataset, which was StegoGAN, was able to compete with the original paired training dataset as well, with PSNRs of 30 and 31. So these are the problems that we solved. First, pick to fix it assumes bijective mapping, so we moved to StegoGAN, but 2D StegoGAN fails in 3D, so we had to extend it to 3D. But the mask generation fails. We add a stronger mask network. We also implement bijective loss, but even then the network fails. So we have to find a better network, which is MAD unit, which was then trained on the three experiments that I just showed. Now, as for future works, we plan to evaluate it on more publicly available datasets and create a fusion of multiple modalities. So basically, we have any modality that can be translated to any other modality. Using such a 3D translation network, we can have either separate generators or we can create a generated latent space using metric learning. So that's all. Thank you. So these were the inferences that we performed using our model. For instance, these were the results generated during training itself by validation, and these are the results generated by 3D MAD unit, pure vanilla 3D MAD unit. Then first, when we extend it for cycle GAN style training, then after training it for a good amount of time, we start to see these artifacts and hallucinations, and the results have all of these messy artifacts in the CT scans, which should not be there. Finally, when we extended for using StegoGAN training, we were able to solve this artifact problem, and even by the end of our training, these artifacts did not come up, and the results were very nice.